Hello physicists! Today in this video what we're going to be doing is showing one of the many ways in which vectors can be utilized. In this specific problem we're going to be attempting to find the angle between two vectors. Vector A, which is denoted in unit vector notation by I minus 2j plus 3k, and the vector B, which is denoted by 4i minus j minus 3k. What we're going to do is, when drawn in the x, y, z coordinate system, in the rectangular coordinate system, we want to find the angle between them when drawn from a common point. Okay, the origin. So we want to find the angle theta that I have drawn here. Now, first, a good estimation does not really do you that well when you're in the third dimension, because it depends on the point of view that you're looking at. Okay, so what we're going to have to do is find some way to translate this into an angle. And there is one thing you can do. One ingenious thing that you can do is utilize the dot product of the vector. The two definitions of the dot product that we have utilized, because one of them inputs in only the x, y, and z components of the vector, and the other one just requires the magnitude, which we can find manually, and it outputs the angle. So let's illustrate by solving this problem. First, what we want to do is find the dot product of these vectors. So the A dot B, so the dot product of A and B is equal to AX times BX plus AY times BY plus AZ times BZ. Okay, and what we get is 1 times 4 plus negative 2 times negative 1 plus 3 times negative 3. Okay, we get 4 plus 2 is 6, minus 9 is negative 3. So we get the dot product is negative. We get negative 3 as the dot product of these two vectors. Now the dot product can also be defined as the magnitude of A times the magnitude of B times the cosine of the angle between them. Now let's try to find the magnitude of A. The magnitude of A is equal to the square root of ax squared, the x component squared, plus the y component squared, plus the z component squared. Okay, and substituting everything in, we get 1 squared plus negative 2 squared plus 3 squared. Now what does that get us? We get 1 plus 4 plus 9, which is equal to 14. So the magnitude of vector A is equal to the square root of 14. Similarly, we can do the same process. Similarly, we can find the magnitude of vector B, okay, by just squaring each of the components, adding it, and then taking the square root of that sum. Okay, the square root of bx squared plus by squared times bz squared. We get 4 squared plus negative 1 squared plus negative 3 squared. And we get 16 plus 9 plus 1, which is equal to the square root of 26. Now, we have the magnitudes of A and B and the value of the dot product. So this simply becomes an equation that we need to solve. Now, we're given that A dot B is equal to AB cosine theta. Which means cosine theta is equal to A dot B over AB. That's just equal to negative 3 over the square root of 14 times the square root of 26. Now, utilizing a calculator, we get theta is the inverse cosine. The inverse cosine of negative 3 over the square root 3 over the square root of 364. And if you take the inverse cosine of that, we get 99.05 degrees, about 99 degrees, which looks right because angle theta, it appears to be greater than 90 degrees, okay? It's greater than 90 degrees because our dot product was negative. The dot product was negative, so we ended up with an angle greater than 90 degrees. If our angle was 90 degrees, then the dot product would have had to be 0. The dot product would have had to be 0. So one quick aside here, that the one quick way to check if two vectors are perpendicular, if A is perpendicular to B, then A dot B is 0. Because if you try to reverse that process and try to find theta when A dot B is 0, well, the inverse cosine of 0 will always be 90. So if A is perpendicular to B, then A dot B is 0. And in the context of this problem, by using the two definitions of the dot product, we were able to find the angle between two vectors. These two vectors, which we found to be 99.05. Thanks for watching. We'll see you next time.